Part 1 says find the values of theta between 0 and pi that form the portion of the graph r equals 4 cosine 3 theta in quadrant 2. Okay, so let's just first start off by sketching a quick graph of this. So I think by now we kind of have an idea that this is going to be a 3-petal rose curve that's going to have one here, and one here. So they're asking us for this part here. What values of theta make that petal right there? So there's a couple different ways that we could go about solving this. I actually think it's easier if we bring this back to what this graph actually is. So if I were to graph this with r's and thetas, this is going to start up here and it's going to come down because it's cosine, right? And then it comes back up and then it comes back down. And one of the things that we've explored potentially here, I'm hoping, I don't know, I'm filming these out of order, so is that when we have the odd petal, we only need to go to pi, so I can actually stop right there. And that this is half a petal, a full petal, and the other half of a petal. And that those directly correspond to these things over here. So when I start here with a positive radius, and I do this part right here, up until 0, that ends up connecting to this part right there. So I know that this part of the original graph is going to be formed right there. Now the next part here is this negative radius. So I know that I have angles that are up here, okay? And I probably should have gotten into what that is because I don't know whether we know this stuff or not, but you know, if we graph this stuff right, the period would be 2 pi over 3 because we take the b value divided by 3. That means our x scale here is going to be divided by 4, so that's going to be pi over 6. So this is at pi over 6, this right here is at pi over 3, this right here is going to be at pi over 2, I believe. This one's going to be 2 pi over 3, this will be at 5 pi over 6, and this one will be at pi. So I know where all of these values are. So I know right here, pi over 6, that's right here, and that forms this green section. Now from pi over 6 until 2 pi, so that's these angles up here, I have a negative radius. So they're actually forming this part down here. So this whole part is actually forming answers in quadrant 3, the opposite of the angles because we have a negative radius. That means that when I'm here from pi over 2 all the way to 5 pi over 6, so that's right here, I have positive r values, which means that I am, in fact, in that quadrant. So I know that the answer to this is going to be from pi over 2 to 5 pi over 6. So just to kind of summarize this one last time, we have that the graph creates these petals. So this is half a petal, full petal, half a petal, which directly correlates to how this is actually graphed. And when we have negative radiuses, that's going to shoot us into the opposite quadrant of the angles. So once we label all of the angles on here, we can actually very easily figure out which quadrants we're going to be in. Positive, so we're in the exact quadrant these say, so 0 to pi over 6. From pi over 6 till pi over 2, we have a negative radius, so we're going to actually be graphing down in quadrant 3. Up here, from pi over 2 to 5 pi over 6, we have a positive, so we'll actually be where those angles are, which are in quadrant 2. And from 5 pi over 6 to pi, we have negative, so we're going to reflect over here, and it will form this bottom part. 2 is going to be a little bit easier than 1. We're being asked to find the values of theta that form the inner loop of this graph. So if I just quick sketched this graph over here, we know that this forms an inner loop and that it opens up. So it's going to kind of go something like this. Super rough sketch. So what I want to know is what values form this little inner loop here in the middle. Okay? So the easiest way to do that is, again, connect this back to what this graph actually looks like. So if I were to graph this from r and theta, this is going to go like this. And what I'm looking for is these values right here. So the values where r is less than 0, those always form the inner loop when we're talking about these things. So if I can just figure out when r equals 0, I can then use that to help me figure out when it drops less than 0. So I'll just set r equal to 0, so I get square root of 3 plus 2 sine theta equals 0. So that's sine theta equals a negative square root of 3 over 2. So that's in quadrants 3 and 4, and it's going to have a reference angle of 60. So theta is going to be 4 pi over 3 and 5 pi over 3. So I know that right here is 4 pi over 3, and right here is 5 pi over 3. So when theta is in between these values, then we know that it's forming the inner loop of this shape. Now you might be saying, why is this important for us to find these values? And it has to do with this connection to calculus. One of the things that we do later on in calculus, towards the end of the year, is we use calculus to help us find areas or volumes. So in particular, we can use this one to find the area of that inner loop, or for part 1, we could use it to find the area of just one of those petals based on the quadrant. And we need to be able to identify the theta values that create that part of the graph in order to be able to use calculus to find the areas. For part 3, if you've done the Desmos advanced graphing activity, then you should have already been able to see that, and it just leads us into what we're doing in part 4. All right, so this absolute value here is kind of tricky here. We got r equals absolute value 5 cosine 3 theta. All right, so let's actually go about graphing this. If I normally were to graph this, I would have period 2 pi divided by 3, an x scale of pi over 6. So let's just sketch this super quickly. But I'm going to do something a little bit weird. Anytime I go negative, I'm going to put a dotted line when I graph it. So I'm going to go here, and then it's going to go down and back up. So that's one full cycle here. And what I'm going to do is 3 of those, because 3 theta, that means it'll take me 3 full cycles to get to 2 pi. So there's 1, here's 2, and here's 3. So the reason I did those dotted there is because this absolute value is going to reflect anything that was negative. So those actually graph up here instead. So this, which is normally would be a, let's think about this, a 3-petal rose curve, the absolute value is going to actually make this have, this is a half, 1, 2, 3, 4, 5, 6 with the 2 halves. A 6-petal curve, which was previously not easy to get. Once we recognize that this is actually just going to give us a 6-petal curve, what we can do is the same shortcuts we've been doing all along. We can say we know this is 6 petals, which means that each one is going to be 60 degrees apart from the next one. And from there, we can say the max R is going to still be 5. And we want to know where we start. Well, it's cosine, so cosine is 3 theta equals 0, so theta equals 0. So my first petal will be at 0, and then the rest of them are just going to be 60 away. Now you could also figure out where these maximums and are for all of these and use those to plot the points. That's another way. So I'm going to start off here at max radius of 5, and then I'm just going to go 60 away each time. 60, 60, 60 away. There we go. And I'm going to connect them. Now this does graph a really interesting way. I would encourage you, if you're super bored, to just go to Desmos and try graphing these things and compare how they graph. But this one basically graphs like this. So it graphs the entire first part and then the second part, whereas normally our rose curves kind of jump around from quadrant to quadrant. We don't do that this time. Fancy graphs we got going on here. So this is variations on the traditional. So this has the setup like it should be a limacue, except that we have a 3 theta here. So that's going to change what this is altogether. So let's just do a quick little exploration. Its normal period would be 2 pi, so it's going to be over 3. The x scale is going to be pi over 6. So when I go to graph this, it's going to have 3 full periods between 0 and 2 pi. It's 3 theta. Midline is at 3. It's going up to 5, down to 1. It's cosine, so I'm going to go 1, 2, and 3. And what I want to do is actually graph all of these values. So the way that I'm going to actually do this is kind of use this, but use the scale more than anything else, and then the pattern. So the pattern of cosine goes top, middle, bottom, top, middle, bottom. So one thing that I've occasionally done to help me graph this is I actually will mark off where these radiuses are with a little different colored pen, so that it's a little bit easier for me to identify, especially if there's a lot. Okay? And that's going to help me just be able to jump around a little bit more. So I'm going to go start at 5. Then I'm going to go pi over 6 away into the next line, pi over 6 away to the next one, pi over 6 away back to the middle, pi over 6 away to the top, pi over 6 away back to the middle, pi over 6 to the bottom, pi over 6 middle, top, middle, bottom, almost lost that one, back to the middle. So I can just follow this pattern, and this is what this graph looks like. So it looks like a 3-petal rose curve, except that it never actually touches the center in there. So it's pretty neat, I think. I don't know. Maybe you don't. Do the same exact one here. We got r equals 2 plus 2 cosine 3 theta. So again, what I really need to know about this is what the x scale is and where the mins and maxes are going to fall for this. So the period of this would be 2 pi over 3. That means the x scale is still going to be pi over 6. And when I graph this thing, I have a midline at 2. It's going to go up to 4, down to 0. And it's cosine, so it's going to start at the maximum. So this is what I'm basically going to graph. Let's pretend like that looked nice. And I'm going to put my little extra dashes here at 2 and 4. I don't need to put it at 0. And I'm going to attempt to follow the pattern, which is to start at the max, move into the middle. When I'm at this angle right here, I'm going to be at 0. Then I'm going to be at 2, out to the maximum, back to the middle, back to 0, back to the middle, to the maximum, back to the middle, to 0, back to the middle. And you see how I use my finger there to really help me because it gets a little confusing. And this one goes like this. So it looks exactly like a normal 3-petal rose curve, except that the path is completely different. A normal 3-petal rose curve goes like this, starts in quadrant 1 into 3, up into 2, and then ends in 4. This one goes in order. It goes from 1 to 2 to 3 to 4. So it's kind of neat. Alrighty, r equals 1 plus 4 cosine 3 theta. If you guessed we were going to do the exact same thing, you are right, but it's going to be a little bit trickier this time around. So our period is still 2 pi over 3. Our x scale is going to be pi over 6. I really just need to know where the mins and maxes are here. It's going to be 1, 5, and then this is important, negative 3. And this is going to be the hardest part. So we're going to do this much slower, and I'm actually going to probably connect the dots as I go. So start off with cosine. It's going to be out here at 5. When I'm at pi over 3, it's going to be all the way down at 1. When I'm at this angle, it's going to be negative, which means it actually graphs over here. Okay, so far, I'm going to do this in the red pen because it gets a little bit, it'll be too thick, I think. It goes like this. Okay. Next, when I'm at this angle right here, I'm back to 1. So that means I'm going to have a point right here. So this is going to connect back through and then hit that point there. So it's kind of weird looking so far. Next, we'll be back out here at 5. Here we'll be back in at 1. Okay, so if I connect those, it's going to go like this so far. When I'm at this angle, it's going to be at negative 3. So that's 1, 2, 3 in here. So when I connect that, that's going to go like this. Okay, and we got this very weird stuff going on here now. Next, I'm going to be out here at 1. So when I connect these, it's going to loop around and then exit out and be right there. Here, it's positive 5, so I'm going to be right there. We're going to start seeing the shape now, I think. Next one is right here. We're back at 1. Okay, so this is going to connect here. So we have this inner loop inside of the big petal. Crazy. Let's see. This one right here, we're going to be at negative 3. So that's going to be right there. So when this one connects inside, it creates that shape right there. And then we will end up at 1 before we connect ourselves back to the start. So one of these petals, what it actually looks like is this. Okay, that's what's happening here. So we have one over here that's really big, and then we got this little mini petal inside. One over here that's really big with this little one inside. Okay, so let's compare what's going on with all 3 of the ones that we just did to see if we can come up with some shortcuts. So first we have the shortcut of how to graph it by just kind of using the scale to help us graph it. You can't see all these at the same time, my bad. Let's just start with this one. Here it touched 0, 0, that's when A equals B. This one, notice how we have no negative radius. It did not touch in the center. Okay, so this one has the gap in it. These guys, we had negative radiuses. If I had graphed the cosine, these negative radiuses here, they create these small petals versus the larger petals that are right there. Okay, so we got little petal, little petal, little petal, and then we got the big one, big one, big one, and that's the other half of the big one. And that creates these. So it's pretty easy to identify actually by just looking at the A and the B value, what you got going on. Okay?